why don't we continue? And I'll probably try to go through this part a little quicker since we have to be done by 5:30, and I want to get to some of the results from some of the recent simulations. So this second part addresses some of the high-performance computing issues for CFD simulations, in this case, turbulent combustion. And so about 10 years ago, there was an issue of whether we could scale directly from the petaflops machines in 2010 to exaflop machines, 10 to the 18 floating point operations per second in the 2020 type time frame. And that would represent about a 500-fold peak increase in performance. But the problem is that the usage would not allow us to scale up using current technologies, off-the-shelf technologies. And so as such, there's been a lot of effort within the DOE, both in NSA as well as OSCAR, the Advanced Scientific Computing Research Office, dedicated to computer science research to figure out how to develop hardware that would allow us to stay within about a 10 to 20 megawatt footprint for power usage at these high-performance computing centers, rather than taking commodity processors and scaling those up, which would require the power of something like Hoover Dam gigawatts to power a supercomputer, which is not viable financially. And so some of this research computer science research predominantly has been focused on development of computing on a node, interconnects that avoid latency, and how to get faster storage. And many of the issues with scaling to exascale have to do with extreme parallelism. So because the frequency of processors have kind of stalled out, the only way you can get up there is to have lots of them. And so we're talking about maybe billions of processors, concurrency to get to exascale. We also have issues with data motion. So it costs energy to move data on a transistor or on a chip, just a few millimeters. In fact, where it used to be that the computation itself was what was most costly in terms of energy use. Now, that has changed to the point where moving data across within a node as well as across the interconnect of the machine is extremely expensive from a power standpoint. And then the low power kinds of processors that are commodity today that we have on our portable devices are the ones that HPC is also using. So these are the accelerators and heterogeneous machines that have both CPUs as well as GPUs and various other types of computing devices, resources on them. And so figuring out how to program that effectively beyond just simple MPI between different nodes. I talked about OpenMP and things like OpenACC or OpenMP 4.5, various other pragmas that allow you to program these accelerators, or even down at programming in CUDA, makes it more of a challenge for domain scientists like us to use these machines effectively. And then lastly, just because there's so many parts on these HPC machines, there's an issue of reliability and resiliency. So how do you progress your computation when there's going to be a failure, mean time to failure of one of the processors, or some part of the machine is much shorter? As I said, the issue in moving towards exascale and beyond is an issue of how to manage data locality because of the energy cost of moving data. And this plot kind of shows you that the number of picojoules per operation costs as more now to move 5 millimeters across a chip, like 50 picojoules per operation, compared with the energy to compute a floating point operation, which is about 10 picojoules. And so we have to worry about data more than we have to worry about compute. And so you've probably heard the phrase that cycles are free, but data movement dominates the problem. I've already said this. The way to get to larger computing is increased concurrency, up to 1 billion processors, maybe at the exascale. And so DOE has, since about 2010, supported various exascale computing initiatives that include applications, system software and hardware development, and also system integration. And one of the applications that they supported is combustion. And so we had a co-design center that looked at co-designing both the algorithms, the system software, as well as the hardware on an interdisciplinary team. And that's the message I kind of want to pass to you all today, is that to get your codes to scale well on these heterogeneous machines that we're moving more towards in the future is no longer a single person endeavor. You really need to have a multidisciplinary team of computer scientists, domain scientists like ourselves, or engineers, and applied mathematicians working closely together on a problem. And so that's an issue. Or communities need to have, maybe not just individual groups, but overall communities need to have more activities like that for everybody in the community. I've discussed this, so let's see. This has all been talked about. Just want to see. So the old constraints that we had with computing is that throughput and peak clock frequency was the main limiter for performance improvement. Flops used to be the biggest cost for a system, so we would optimize machine hardware, systems, software, and our application codes for compute. We had modest growth in parallelism by adding nodes, and we could describe our codes with MPI plus X model, where X could be OpenMP or OpenACC. And we had more or less uniform costs for computing within a node and also between nodes on the interconnect. The memory scaling, that is the byte to flop ratio, capacity and bandwidth, has remained nearly constant. And so there was an era before 2010 or so that we had assumed pretty much uniform system performance. However, now we have to reason much more about how we express data locality in our algorithms, sometimes at the expense of flops and independence. We have to find ways to express huge, massive amounts of parallelism, both data parallelism that I talked about before, where we divided our domain into little chunks, but there's also opportunities for task parallelism. If you can identify which parts of your code can execute at the same time without interfering with one another. For example, a lot of the chemistry and thermochemistry could be evaluated at the same time, but we don't do that. We just currently loop over all species and loop over all reactions. That doesn't have to happen because a given species only participates in a handful or so of reactions at a given time. We need to figure out ways to minimize data motion. So while the data is sitting in your memory registers, reuse that data as much as possible and find algorithms that allow you to reduce any kind of synchronization. So for example, spectral methods or FFT methods would be very, very bad or poor. It would perform poorly on machines that had to synchronize frequently. So, and then lastly, we had to find methods that are more forgiving or at least could detect and address faults on the machine. Did you have a question? No? Okay, just yawning back there. Okay, so we formed this co-design center that had computer scientists, math people, and domain scientists, and also interacted directly with a lot of the HPC industry vendors themselves that were developing hardware for next generation machines. And so this co-design center where the hardware vendors inform the algorithm designers of their constraints and limitations with the hardware, and combustion or domain scientists tell them about what's possible with numerical algorithms. And we iterate on this together. And so we had this kind of methodology that I think has stuck within DOE, where you develop applications that are then represented more simply as proxy applications. That is, you write software that represents pain points or critical paths that are in your large applications in terms of the performance. And then at the other end, the hardware guys, the architecture guys, also do DNS, but they do DNS of their proxy architectures and how different different pieces of the hardware perform for a given set of use cases of proxy apps from the domain side. And so we do this iterative loop where they make measurements of models and simulations to tell us about performance and different execution model trade-offs, and then tell us that we should be, if we give them algorithms that are less bulk synchronous and that are more asynchronous, that they'll perform better on these types of machines that have lots and lots of latencies. So we go around this loop lots of times, and that's what's known as application co-design for computers. One of the outcomes of this co-design work is the development of a new set of codes, and also a testing and evaluation of a new programming model that was developed at Stanford called Legion. And it's an asynchronous rather than synchronous programming model that does deferred execution, and it has the ability by the runtime and the compiler to hide latency so that us as the user don't have to worry about that. We also are developing a low-mock and a compressible adaptive mesh refinement code because we want to move up in pressure where these devices operate. And the AMR lets us apply mesh where it's needed, where you have high gradient regions in flames and in ignition fronts. And I'll skip this. So I want to talk a little bit about the programming environment that we did look at. And this is something that we should all think about. So our job as engineers is to write accurate, functionally correct application code. And then we need to map that code, oops, wonder what happened here, to target machines. And we have to extract, this didn't work out, parameters. Oh, I know why. Hang on. Sorry for this. Let me move to a different one. This will let me do it better. Okay, apologies. Okay, so we need to write functionally correct application code. We kind of have the responsibility right now to map that code to a given target architecture, whether it's CPUs or GPUs or something combined. We need to figure out ways to extract parallelism. So I showed you how we did data parallelism simply on a uniform mesh code. And then we have to manage how data is transferred across a node, across the interconnect between the GPUs and the CPUs. And we have to schedule the tasks in a way that hides latency. So we, a lot of times, have to come up with algorithms that interleave communication and computation to hide the cost of moving data around on the machine. And then at the end of the day, for example, in an AMR code or other codes that are data-dependent behavior, you have to do this all over again. And so it's no wonder that we walk away at the end of the day very frustrated because of this huge task of writing code. And so what would be ideal is to have the compiler runtime have a holistic, higher-level view of the data and where it sits on different resources of the machine. And our job would be to still write functionally correct application code, map it to the target machine, And then separating concerns, we should not have to worry about the rest of it. That should be left to the job of the computer scientists to do from a compiler runtime standpoint. And so one compiler runtime that starts to look at these issues, and there are many of them out there, this is just an example, is the Legion programming model. And this is a performance-oriented, portable, productive compiler runtime. It captures the structure of the data, and it also decouples how you map the data and the tasks onto the memory hierarchy and onto the processing resources of the machine. So it's not hard-coded or hard-baked for a given architecture. And it has a way to then automate how data is moved around, how parallelism is discovered, how synchronization is done between tasks, and how to hide latencies or failures on the machine. There's also support here for both task as well as data parallel forms. And while co-design with proxy apps, which are smaller pieces of code, gives a lot of information, what we worked on together with the CS team was to take our entire S3D DNS code, a full application, and port it to this new way of programming with asynchronous Legion. So a little bit of description about Legion. It describes the data with logical regions, which are an array of objects that don't have any implied layout or implied location. They're described by an index space, a set of keys. This could be your mesh. They're described also by a set of field spaces. These could be all your dependent variables or fields, your scalar variables, your velocities. And then the operations that you can do on these logical regions are to split them up, partition them into subregions. And you can do that recursively, for example, in an adaptive mesh refinement code as you go to finer, lower levels of coarse down to fine meshes. We can also slice by fields, not just by the mesh itself. So you can look at operations on only certain fields of a given subfields, certain scalars, for example. Similarly, the Legion tasks are a hierarchy tree of tasks. The tasks, these would be your functions or subroutines now, have to specify the subregion that's being used, the field usage, and the access modes, whether you're going to read the data, write the data, or read-write, or do some kind of transformation of that data. And so this is an example of how the Legion runtime works. So for example, if we have two tasks that both want to use a certain region, R, but they're going to use different fields of that region. So the runtime would recognize that these two tasks are operating on disjoint data. For example, task 1 wants to work with field A and task 2 with field B only. Task 1 in a read-write access mode and task 2 in a read-only mode. And so Legion runtime would be smart enough to schedule these two tasks independently and have them run at the same time on two different processors, node 0 and node 1. Now, if we change the problem a little bit and we add that task 1 also wants to do something, transformation of field B in addition to field A, then the runtime would recognize this and realize that you can't you can't run them at the same time, task 1 and task 2 anymore, since there's a dependency. And so task 1 would be executed first, since it appears sequentially first. And then the results of task 1 would be copied over to task 2. And then task 2 would run on node 1 after the computation was finished with task 1 on node 0. So it has the ability through a task graph, a dependence task graph that it analyzes dynamically to be able to schedule the work, the tasks on different resources of the machine and know about when the dependencies between the data and the tasks. As I said earlier, the Legion system also has a separate mapping interface. So the application scientists can write policies or guidelines on where the tasks should run and where the region should be placed. And so you can think of the different computations being placed on CPUs or on GPUs, and the data being placed on different types of memory on the machine. DRAM or on RAM on the GPUs. Mapping is also computed dynamically, and so if you're trying to move a code over to a different platform, different supercomputing machine, you don't have to rewrite your code, but you do need to change your mapping interface. So it separates the mapping of the different tasks and data from the rest of the code, which is really nice, and it decouples correctness from performance. So the CS guys ported S3D, which is about 200,000 lines of code, and as I said, the data is these 3D Cartesian grid of cells. Typically, we have about 64 cubed cells per node. Nearly all of the kernels, computational kernels, are acting on a per cell basis. And so it's kind of embarrassingly data parallel. And we have hundreds of tasks to compute, largely because of the chemistry. And so there's opportunities for a lot of significant task parallelism in addition to the data parallelism. Except that the compute intensity from the original code was pretty low. And that's because we have very, very large working sets per cell, thousands of temporaries that we have to store. And so loading those up into memory and registers is very costly because of the data movement problem. So the performance limiter is data, not compute. And so rewritten in Legion in terms of the tasks, which are these boxes, and their dependencies on one another, which are these lines in this plot, this is what the right-hand side call to the S3D code looks like in the Legion runtime. And we have to execute this 6 times per time step for a 4th-order RK method. And the width of this task graph is indicative of the amount of task parallelism that can be had in addition to the data parallelism that we got from splicing up our domain. And this is for hydrogen-oxygen system. As we move to heptane or PRF, the width of that graph gets tremendously larger. And trying to reason about that mentally is beyond what we can do effectively as people. Machines are much better at that. So the code performance is kind of shown here in this pie chart. Most of the computation goes into the evaluation of the chemistry, shown by the pink get rates, and of the stencil computations, the derivative computations in the dark maroon color. And on the right is a computer science plot called a roofline plot. And the key kernels in terms of cost are the little dots shown relative to the ideal roofline. And so the departure from this ideal line is representative of the inefficiencies of the way the software is written. And so we found that that because we're bandwidth limited, the chemistry and some of the right-hand side stencil computations don't get the performance that is ideal. But still, we get about 85% of the performance on the GPUs. And so on many of these supercomputers, the GPUs account for over 90% of the computational power. So you want to be able to run on these GPUs. One other thing we noticed is that the chemistry, that Legion treats the tasks as black boxes, whether they're computations for chemistry, for fluid mechanics, or for machine learning, it doesn't care. They're opaque to the runtime and the compiler. So it doesn't care how you write the tasks, but you still need to have fast leaf tasks to be computationally efficient. And in our case, that's for chemistry, diffusion, viscosity, and that sort of thing, for different types of devices, compute devices on a machine, CPUs, GPUs, and for multiple mechanisms. And so what we wrote is a domain-specific language chemistry compiler called Singe that evaluates chemistry very fast, taking inputs from Chemkin, for example, for chemistry, transport, and thermo. It runs it through this DSL Singe, and it emits very fast kernel code for different types of architectures. It emits fast CUDA code for GPUs and fast AVX SSE code for different kinds of CPUs. And one of the challenges is that GPU programming models currently emphasize computational throughput, which is not always the best choice for performance, especially when you have large working sets like we do. PRF needs something on the order of 1,700 double precision reaction rates per point, whereas the GPU register file can only store 128 per thread. And so the need right now is to break apart your kernels or fission your kernels into smaller pieces, but that limited by the memory bandwidth, and that's slow because you have to read and write to memory lots and lots of times. And so one idea that the CS guys on our team implemented is what they call GPU warp specialization. And so on GPUs, you can leverage the underlying structure of the GPU hardware. And currently, GPUs execute processes in streams of 32-wide vector instructions. All threads on the warp execute typically the same program, so it's a data parallel unit. But that's not really needed. You could write code that specializes each warp and leverage the task parallelism. And so different warps on the GPU could do different computations acting on the same data, which lets you have much better use of the memory while also keeping the processor busy. And so that's what we did, and we ended up getting much higher performance and rates and speed-ups of our chemistry evaluation than the way we used to do it. Another reason to use asynchronous task-based programming models is that as we move more towards data-driven methods like machine learning and regression methods, and in this example, we did an eigenvalue solve, eigensolution of the chemical explosive mode, which is kind of expensive if you want to do it frequently over all of the mesh points. And so as an in situ analysis method, we let Legion figure out how to code up the CEMA methodology, which is basically analyzing the reaction rate Jacobian to help us identify flame fronts, crossings for reaction fronts and flame fronts. And we wanted to run CEMA at every time step as a diagnostic tool to allow us to steer where and when we need to adapt the mesh. And the problem was that the eigensolution took longer than a single explicit Runge-Kutta stage, and so you'd have to, if you were to write this code by hand, you'd have to divide up the CEMA analysis across multiple Runge-Kutta stages and then have to interleave those computations with other computations so as not to impact the solver and other critical operations of the solver. So that would have been really hard to schedule that by hand. But with the runtime doing the asynchronous task execution and dependence analysis, it's able to schedule this eigensolution on the CPU resources that weren't being used as the computation was proceeding. And it took just a few days to implement rather than probably several months to do it by hand. And so I just want to give you an idea of the performance that we got from this S3D Legion performance compared with our MPI code. This is the weak scaling showing the throughput on the ordinate plotted versus the number of nodes on Titan, which is a petascale machine at OLCF. And the blue diamond symbols represent the Legion code, which has higher throughput than the MPI Fortran code shown by the red triangles. And at low node counts, we got about a 4x speed up rewriting our code in Legion compared with the original MPI code. Whereas on very large node counts, upwards of 13,000 nodes, we were getting even better performance and 7x speed up. And that was because Legion was able to hide the latencies of moving data across the large distances across the interconnect by scheduling different tasks to execute to compensate for the latencies. And so I think this is a good result. And we also compared the execution of the analytics, in situ analytics, without evaluating CEMA, shown by the red bars on two different machines Pisdane at ETH in Zurich and on Titan at OLCF. So red represents just the solver, no SEMA, and the blue represents the in situ SEMA analysis. And so you can see that the SEMA costs about an extra second or so compared with without doing the analytics, and a fraction of a second on Pisdane. But when you, this is in the Fortran code, but when you write the SEMA analysis or have it scheduled by Legion, we get a 84% reduction in cost on Titan and a 90% reduction. So it's virtually free to do the SEMA analysis using the Legion code on Pisdane. And so then I guess I want to, well, I'm going to skip all this and then say that we learned quite a few lessons from this computer science exercise. We showed that the potential of doing data-centric, task-based models is the way forward on these heterogeneous machines where we have all kinds of latencies. And it enables new simulation capabilities, not only solving for the physics, but also including in situ analytics. And as we move forward and doing more deep learning methods in tandem with the simulation, I think coding in this style will make it simpler. The code is easier to modify and maintain. Porting to a new architecture is writing a new mapper, tuned for performance on a given architecture. New functionality for the code now just means writing new tasks. We don't have to rewrite the entire code every time we have a new machine. And the runtime would then figure out the dependencies dynamically and schedule the tasks for us. The productivity requires a higher level abstraction layer for scientists to write in, so we don't have to, we can actually take advantage of this separation of concerns where we only write code that we understand in sequential languages, and then the compiler runtime takes care of the stuff underneath. And I think the notion of working together with computer scientists and mathematicians is a good one in this sense of co-design. These problems would have been difficult to tackle on our own. So let me, I don't want to talk about visualization, but I'd like to move on to some of the results that we get from these calculations. So let me go to part 3, since we only have a little over an hour. So I'd like to now transition and start talking about some of the kinds of things we can do with the DNS and the results we're getting. So in the next 3 parts, I'm going to talk about the notion of lifted flame stabilization when you have a hot co-flow that helps to stabilize the flame in part 3. In part 4, I'd like to talk about autoignition in sheared flows and jets that are relevant to engine diesel combustion. And then in part 5, I'd like to talk about turbulent premixed, lean premixed combustion under very intense turbulence conditions. It's relevant to gas turbines. So let's start with the lifted flames. And I'm going to describe results from 3 different lifted flame studies that were made. One in a lifted reactive ethylene jet flame in a hot co-flow. The second one in a hydrogen lifted hot co-flow. And the third one in a DME, dimethyl ether jet hot co-flow at moderately high pressure, 5 atmosphere, where we have low temperature ignition helping to support hot flame stabilization. So let's start with the first one, which is the ethylene lifted jet in a hot co-flow. And as I said earlier, this is relevant to diesel jets. So for example, this is what people are trying to understand is what is the role of lifted flame stabilization, role of ignition and hot ambience for lifted flame stabilization. So this is a movie that I'm going to play from an experiment showing the chemiluminescence from a diesel liftoff stabilization with diesel fuel at ambient oxygen conditions at 850 Kelvin ambient and 35 bar that was performed at Sandia by Lyle Pickett. Okay, so why isn't it playing? Don't know why the movie's not playing. Well, if you could see it, I don't know why it's not playing, even though it lets me click. You would see the direct injector here on the left. The flow would issue from left to right. And you would see, as outlined by the purple line, the edge of the chemiluminescence signal, a bouncing jet that's moving upstream against the oncoming turbulent flow. And periodically, what you would have seen is ignition kernels, hotspots that appear disconnected from the main body of the flame that appear upstream of the lifted flame base. And that they either, these little pockets then merge with the lifted flame base as they interact with one another. Sorry that the movie doesn't play. Try one more time. No. And so if you take that time-varying picture and you plot the liftoff distance from the injector versus time, taking the leading point and watching that in time, what you would get, and what Lyle measured, is this, this time trace, where you have rapid upstream motion of the lifted flame base, followed by a slower migration downstream, and then you would get fast movement upstream. So you get this sawtooth-like structure to this time trace. And I think the fast motion upstream is probably due to autoignition, and slower movement downstream is probably due to diffusional transport as in a flame. So to try to examine what is going on at that lifted flame base, we performed DNS of a lifted ethylene jet flame. And the domain size here was 3 centimeters by 4 centimeters by 0.6 centimeters. And it took about 1.3 billion grid cells to resolve the flames and the turbulence. The flow velocity was relatively high. It was 200 meters per second. And the co-flow velocity was a tenth of that. The nozzle size, this is a slot jet, by the way. So the slot width was 2 millimeters, so it's pretty small. And at this time, I guess it was back in several years ago, we were looking at jet Reynolds numbers of about 10,000, able to simulate that for about 0.15 milliseconds, which represented 3 flow-through times through that domain. And this was a cold ethylene jet that was heavily diluted with nitrogen, 18% ethylene and 82% nitrogen at 550 Kelvin, where the stoichiometric mixture fraction through the dilution was brought into the shear layer and the jet, so that it had very strong interaction with the turbulence. The detailed ethylene air chemistry was 22 species, 18 global reactions, 201 steps, and the heated co-flow was pretty high at a high temperature of 1550 Kelvin. And at that temperature, which is well above the temperature where ethylene ignites, you'll see that the stabilization, the role of ignition in stabilizing that flame is a lot. So this was performed at Oak Ridge on 30,000 cores and with about 7.5 million CPU hours. And it generated 240 terabytes of data. And we also had Lagrangian tracer particles in there with 50 terabytes of particles. So I just want to give you an idea of the dynamics of this lifted flame base. And so on the left, what I'm going to show you is the temperature evolution, red being hot, green being cold. And on the right, I'm going to show you the mixing rate as depicted by the scalar dissipation rate of the mixture fraction, which is causing the flame base, the high temperature regions in red, to bounce around a mean position. So I don't know if you saw that, but here's the temperature. So if you focus your attention on the lifted base, right here. And on the left and right side, you can see sometimes there are these disconnected pockets that are, I think, autoignition pockets that are interacting with the lifted base. And that's being modulated by the turbulent mixing, which is shown on the right by the dissipation rate again. Okay, and then if we compare the next animation shows the HO2 species, which is an ignition marker ahead of the flame compared with the temperature. And so you can see that some of the intermediate species that are due to autoignition, like HO2, formaldehyde, appear much farther upstream than the temperature or OH. And so it's preparing the mixture soup for helping to stabilize the lifted flame that's trying to propagate into this soup of radicals and intermediate species. Okay. Now, if we take a slice of this data, instantaneous slice, this is the second bottom row, we can see what the species mass, the temperature on the left, the, let's see, what is this? OH radical next to that. Formaldehyde species, which is similar to HO2. It's an intermediate species formed from ignition on the rich side of the flame in the third column, and HO2 in the final fourth column. So we have access to all of these species in our simulations. And plotted on top of that is the stoichiometric isoline showing the ratio of the fuel to oxidant for complete combustion. The top row represents a Reynolds averaged picture of this 3D flame. And so you can see the lifted flame base on average sits about 6 jet widths downstream of the inlet, and that the formaldehyde and HO2 and other reactive species mean height sits up further upstream. We can also use DNS to understand how that flame is stabilized by plotting the time sequence, upper row followed by the bottom row, of the OH radical, which is an indicator of the high temperature flame and something that can be measured experimentally. And on top of that, we've overlaid the velocity vectors locally. And this, again, is a slice through this three-dimensional slot. So what you see is you evolve in time, and the black line, which is kind of hard to see, is the stoichiometric mixture fraction isoline. What you see in time through one cycle is that the lifted flame base sits here at this early time, and then you see a very faint appearance of OH disconnected from the main body of the flame farther upstream, which is a developing ignition kernel or hotspot that's accumulating radicals and heat. And then it further develops, and the flame starts to move upstream. The kernel gets bigger, starts to propagate outwards from where it was formed, and then by this time, some fraction of a millisecond later, it's merged with the kernel is merged with the main body of the flame, similar to the movie I would have showed you from the experiment. And then finally, you see the flame moving up, propagating upstream, or being advected upstream, and then the cycle will repeat itself. We can analyze more quantitatively the evolution of that in time of the stabilization point by plotting the axial position of the most upstream point of the stabilization point in time, similar to that time trace we saw from the experiment. And here again, you see kind of a sawtooth-like shape where you have very fast upstream migration followed by slower downstream migration. And these upstream fast migration doesn't have any kind of regular period to it. It kind of just happens randomly. And what we found is that when we analyze how fast that upstream lifted flame stabilization point moves relative to the local gas velocity, so that would be the displacement speed of the tip of that flame stabilization point relative to the local gas velocity normal to the flame front, which we're denoting by some iso surface low value of the isosurface of OH radical, then we can look at the budget for the displacement speed, which depends on the reaction rate locally and on the species diffusion. If we plot the displacement speed in the second row here in time, we see that the displacement speed shown in the blue dashed line is very high, over 100 meters per second, at the times when you have upstream migration. And so for the speed of that front to be so high can only occur if reaction is significant in the absence or with negligible diffusion transport. And so that's indicative of a auto-ignition, spontaneous ignition front propagation that gives you that fast upstream motion. Whereas very quickly after it propagates upstream, the displacement speed of that front relaxes drastically back down to values that are indicative of some sort of flame propagation speed where diffusion and reaction are balanced. And so there you see the slower migration back downstream, and then again you see a very fast speed happening sporadically when you have spontaneous ignition. So from these statistics, we concluded that there's this conceptual stabilization mechanism, and Lester Su and Godfrey Mungall had described this earlier for lifted flames in the absence of heated cold flow. And so what we find is that initially you have ignition occurring under very lean mixtures with low scalar dissipation rate, low mixing rates. And so this is the preferred mixture fraction where ignition delay in a homogeneous mixture would ignite the soonest. We don't see self-propagation upstream with the mixing structure, which is that of a jet. And this is what Mungall's diagram of this looks like. You get these coherent jet structures that shed with the preferred frequency. But rather we have the ignition, the kernel, ignites in lean mixtures, and then it is advected upstream very rapidly due to the turbulent structure. And then occasionally we see local extinction occurring by high scalar dissipation rates of the flame, or by flame shortening as the point is convected downstream. And then in the next part of the sequence, we find that ignition occurs in the next subsequent coherent jet structure, and this cycle kind of repeats itself. We also did a chemical explosive mode analysis, and I mentioned earlier that that is a technique that Tianfeng Liu developed with Ed Law that looks at the reaction rates of the chemical Jacobian. And positive eigenvalues represent explosive modes that, if you didn't have any diffusive losses, would self-ignite and be explosive. And negative values are those exhausted modes that, for example, that you would find in mixtures that are post-ignition or in product gases. And we can look at the eigen solution in terms of its structure to construct what's known as an explosion index for species based on the diagonal of the product of the left and right eigenvectors. And that gives you the correlation of species aligned in the direction of the most explosive mode. I should say before this that the explosive mode, the transition from positive to negative eigenvalues is a quantitative measure of where your reaction front exists. So in a flame where you have reactants that are not reacted, you have explosive modes with large positive eigenvalues. But once they've reacted, you form product gases, and those have negative eigenvalues. And similarly for ignition fronts. And so this is a good metric to demarcate the reaction front by looking at the zero crossing of the eigenvalue. So we took this lifted jet flame and applied the CEMA analysis. And this is the CEMA explosive modes that are positive are shown in red. The exhausted negative eigenvalues are shown in blue. And the transition between red and blue denotes the lifted flame base. And shown here, and the red upstream regions in the shear layer that are highly reactive are shown by these bright red regions here. This is the chemical explosive mode in the absence of any kind of diffusion. If we convolve the ratio of the explosive mode with the diffusion, then we can construct a local Damkohler number, which shows you the action of the coupling between the chemical rates and the local mixing. And we can once again see similar structure where you have crossing between red and blue here, and the highly reactive shear layers or mixing layers upstream on either side of the jet, followed by downstream exhausted modes that are shown in blue. If we compute the, it's hard to see up there, the explosion indices or explosion pointers, we can also identify the controlling species that are aligned with the most explosive mode and the temperature. And so what I've plotted here, I've taken that jet and flipped it over on its side. And what's shown here is that in red, that is the temperature in red. HO2 is in green, OH is in blue, and CO and another intermediate species, methoxy peroxide, I think, CH3CHO is shown in cyan and gray colors for CO and the intermediate. And you can get a sense of that in an in the autoignition layer, that OH is the main contributor to the explosive mode. HO2 in green is dominant on the rich side. O atom is dominant on the lean side, as shown by the dark navy blue. And then temperature is the main contributor downstream, located between the jet core and the rich flame front, shown in red. In the diffusion flame that trails behind the premixed branches, lean and rich, at the stabilization point, you have a lot of CO and CH3CHO being important. And these are some of the controlling species for fuel oxidation, which is then choked by the slow diffusion. So that's a kind of quantitative metric that you can use to understand the relevant species and also the counterpart, the relevant reactions that are occurring both spatially as well as temporally. Let's see, how are we doing for time? Okay. So if we switch over to hydrogen air rather than ethylene and have a comparably high jet velocity as before and low co-flow velocity, but this time we haven't diluted hydrogen quite as much, and the co-flow temperature is much lower than in the ethylene case. We had 1500 Kelvin in the ethylene case, and so it's not surprising that the autoignition played a significant role in stabilization of that flame. But here the co-flow air temperature was at 1100 Kelvin. The stoichiometric mixture fraction here is at 0.2. So again, we moved, by diluting it with nitrogen, the mixture with nitrogen, we moved the flame closer into the shear layer so that you could have more significant interaction between the turbulence and the lifted flame base. Because normally, if you don't dilute it, the stoichiometric mixture fraction sits out at about 0.05, so way out on the lean side where everything is kind of laminar and lazy. So you're not going to see very exciting dynamics. So I don't want to belabor the point because we kind of went over it with ethylene, but I want to say that here, again, as with ethylene, the flame base stabilizes in the lean mixture. And HO2 radical is very important in hydrogen-oxygen systems for autoignition. It acts as a capacitor or storage unit for storing radicals before you get high-temperature branching. And so we see evidence of a lot of buildup of HO2 upstream of the high-temperature radical OH. So you can see in this image of slice out of the 3D data that the OH, denoting the high temperature lifted flame base, resides here, whereas HO2 is appearing far upstream of that. And it's a precursor of the, as I said, the hot ignition in HO2 chemistry. What we see a little bit different than before for this hydrogen-oxygen system, if we plot the axial time trace of the liftoff point, what we see is not so much the sawtooth-like structure we saw before from the fast ignition and then slow propagation back downstream, but here you see more of like a chain link fence kind of thing. You see a slower migration upstream and then a slower migration downstream. And, and so the difference here is that the stabilization point is not necessarily autoignition so much as it is premixed flame propagation or partially premixed flame propagation following a coherent jet structure. And like before for the ethylene case, we also have occurrences of local extinction when the turbulent scalar dissipation rate or the mixing rate is really high, and that causes the front to then move downstream. And then we see some evidence of ignition occurring again in another coherent jet structure, and this kind of repeats. This is just a close-up view of what this time trace, which is more gradual, both upstream and downstream. And like before, the propagation speed of the liftoff point relative to the local gas velocity, SD, does have values that are somewhat high in some instances, upwards of about 40 or 50 meters a second, which is not indicative of, it's indicative of more of a autoignition, spontaneous ignition front, but on average, it's much lower than before from the ethylene flame. It's closer to about 10 meters a second. And then the local gas velocity, shown by the dashed line, on occasion is larger, negative value than the propagation of the flame front itself, and so that leads to local quenching. We tried to correlate the movement of that stabilization point, fluctuations in the stabilization point, with the axial velocity correlation from a power spectrum analysis across the width of the jet. And this frequency plot shows a preferred frequency or Struhel number that coincides with the shedding frequency of the underlying jet structure. And we also performed some statistics in the vicinity of the lifted flame base, showing that the flame base for these conditions moved about 1 jet height up and down, and that the preferred mixture fraction here, if you look at the isolated near the flame base, is very lean. So ignition was happening under extraordinarily very lean conditions, coincident with the minimum ignition delay time from a homogeneous reactor simulation, and that the mixing rates, the PDF of the scalar dissipation rate in the liftoff region is pretty low. So on average, it's about 10 to 100 inverse seconds, which is fairly small compared to where it's valued in other locations. And the Domkohler number locally here is quite large. It's of the order of 10. And so it's a very robust igniting kind of ignition front with these large Domkohler numbers near the stabilization point. So we then moved on to looking at DNS in a lifted dimethyl ether jet flame, also in a hot coflow, but at a slightly elevated pressure. And here, the lifted flame base looks a little bit different than before. and especially here, we started to see the appearance of what's known as edge flames. These are partially premixed flames that have a rich branch, a lean branch, and a trailing diffusion flame under ambient temperatures. And so it's otherwise known as a triple flame or tribrachial flame under ambient conditions. And the triple point is where the intersection of the premixed lean rich branch meets with the diffusion flame. And the images on the right are from experiments a long time ago by Phillips in 1965. These are Schlieren images showing evidence of this kind of triple flame or edge flame in a shear layer where you have air, oxidant on the left side of the shear layer, and fuel on the right side. And as you strain or change the mixing width, then the layers, the different branches come together. And so rather than being a spread out triple flame with a wide mixing width, they can come together and actually merge so that in a highly turbulent environment, it may look simply as an edge, like a straight line that disappears at the edge. So what we were interested in looking at is what happens when you have flame stabilization in the negative temperature coefficient regime. This is an ignition regime where at about 750 to 900 Kelvin, where the ignition delay actually increases with increasing temperature. And we also were interested in ignition systems that had two stages. So you undergo low temperature ignition followed sequentially by high temperature ignition. So this is a 0D reactor that shows the ignition delay time plotted versus the mixture fraction. And the first stage, low temperature ignition, has a preferred mixture fraction, minimum ignition delay time at a mixture fraction of about 0.4, close to the stoichiometric value. And then the hot ignition for DME here occurs slightly rich, under slightly richer conditions a little bit later in time. And the images on the left show the evolution of the temperature from the 0D reactor, showing a slight increase in temperature of maybe 100 degrees or so, a couple hundred degrees during low temperature ignition, and also the formation of methoxymethylperoxy and its movement as a wave or cool flame as it propagates. And then subsequently you see the appearance of high temperature ignition species like OH that appear following the low temperature ignition. So we kind of repeated a similar experiment to what Phillips did earlier with the laminar flame first with DME. This is with Alex Chrisman. And this was done at much higher pressure at 40 atmospheres. Actually, in this case, we kept the velocity the same. Even though we had a scalar mixing layer, we assumed a uniform velocity profile. You could have also changed the velocity, had a momentum shear layer, but we chose not to. And the interesting thing that we found when we move into this NTC, negative temperature coefficient conditions, and two-stage ignition is that the structure of the flame front changes depending on the temperature, ambient temperature. So when the ambient temperature is about 900 to 1,000 Kelvin, you start to see the triple flame that we saw under ambient conditions previously, with the three branches, rich premixed, lean premixed, and trailing diffusion flame, and triple point where they come together. But you also see two additional branches upstream. And what we found is that you have, on the left is the oxidant, on the right is the fuel, that under fuel-rich conditions upstream, you have this low temperature heat release reaction branch, and then you see under high temperature lean conditions this second, or I should say fifth branch, upstream for the NTC regime. And so you can have up to 5 branches. So we term this now, this kind of flame structure, a poly-brachial flame that can be anywhere from 3 to 5, depending on the ambient conditions. And so our next step was to look at how this kind of jet structure, lifted jet flame, behaves in the presence of turbulence, in the presence of a mean velocity gradient, or shear, mean shear, with negative temperature coefficient and with low temperature heat release. Okay, so our DNS strategy, since we couldn't include the long ignition delay times of the entire 2-stage process, is we cooked up a soup by running a reacting 1D mixing layer of the fuel and air to use as an initial field for pre-processing the DNS data. And we use that as feed data for the turbulent DME simulation. And so, so here's our reacting 1D mixing layer, and we let it cook this DME mixture at 5 atmospheres, heavily diluted DME, 0.1% or 0.1 DME and 0.9 nitrogen at 500 Kelvin. And then the oxidant stream was at 1,000 Kelvin. And we ran it for up to 5.4 milliseconds and started to form low temperature species and a little bit of heat release. With that soup, we then imposed a 3D time-evolving turbulent mixing layer on the DNS to let it develop and interact with this low-temperature soup and let these low-temperature reactions develop with the turbulence. And then we use that to feed the spatially evolving 3D DNS of the lifted DME jet flame. Again, we had similar kinds of domain grid numbers, and domain sizes were small, and we were simulating at very small time steps on the order of a couple of nanoseconds. So this is what the lifted turbulent DME jet flame looks like, where the yellow-oranges just colors is the methoxy-methyl peroxy radical from the cool flame, the low temperature reactions, and the bluish colors represent OH radical, representing a marker for the high temperature flame. And so I want to show you just a quick movie of this if it plays. You can forget about all the words because this was done for another purpose, but I just want to show you the mixture fraction surface will be shown in gray, and then I want to show you the dynamics. So this is the turbulent mixing at the stoichiometric mixture fraction interface. The yellowish colors represent the intermediate low temperature species, and OH is the blue. And so you can see that the high temperature flame is anchored and propagating into this low temperature soup. And the flame base moves, and eventually it kind of migrates downstream since it's so heavily diluted. It's really affected strongly by the turbulence. Oh. So if we compare the statistics between the turbulent and the laminar case, on the left are the conditional statistics of temperature, log of the heat release rate, and the low temperature species with respect to the mixture fraction. And you can see the different colored lines as it evolves from the frozen mixing line, and it starts to ignite under these lean, close to stoichiometric conditions, and then propagates towards richer mixtures in time, or not in time, as you move spatially downstream. And likewise, for heat release, it kind of starts out under these lean conditions, and then it also ignites under rich conditions later. This is in the laminar case. And the low temperature species also forms as a wave. It forms at about a mixture fraction of 0.3, and then later in time it propagates as a wave towards richer mixtures. Comparably, when we look at the turbulent lifted flame at these different downstream cross sections, we see a similar qualitative change in downstream evolution. Starting from the mixing line, it ignites lean, propagates towards richer mixtures. Likewise, the heat release starts about here, and then it propagates and spreads out into richer mixtures. And low temperature species builds up. So I think there's some evidence that there may be this poly-brachial structure at the lifted flame base. We analyzed then the downstream flame branches more quantitatively by segmenting out local reaction zones, as you can see here, from a Marching Cubes algorithm, segmented on temperature being greater than 1,000 Kelvin. And then we also looked at the flame index, which allowed us to distinguish, which is the dot product of the gradient of the fuel with the gradient of the oxidant. And its sign, if it's positive, that means that the fuel and oxidant are aligned together, so it's premixed. And if they're in opposite directions, then you have a locally non-premixed situation. So if we look at two different axial positions, 6 jet heights and 16, where 6 represents close to where the mean flame stabilization point is located, we looked at the PDF of the heat release rate at this near the stabilization point, and we find that there's a peak at very, very lean conditions and also at less lean conditions. And that's shown by the conditional mixture fraction, which is lean at about 0.25 for this peak and about 0.3 for the less lean peak, where stoichiometric is 0.4. We also computed the conditional flame index, and again, it's positive values at both peaks and heat release represents a premixed flame. So that kind of tells us that the structure of the turbulent flame base has both an ultra-lean and a lean premixed branch. If we move downstream away from the lifted flame point, what we are looking at comparably in the laminar structure is a cut through here where the triple flame would exist. And indeed, that's what we find. We find that the PDF of the heat release rate shows 3 peaks, one at lean conditions here, this is mixture fraction, one that represents the trailing diffusion flame at stoichiometric conditions, denoted by the mixture fraction PDF, and one at rich conditions. And that the flame index shows that the lean and rich peaks coincide with premixed combustion, given by the positive flame index, and the trailing diffusion flame, the gradients in the fuel and oxidant are in opposite directions, so you get a negative flame index. So I think we've confirmed statistically that we do see triple flames downstream, and then we see this more complex two-legged branch upstream with ultra-lean and lean premixed flames. And then lastly, we looked at the flame, how fast it moves, how fast the stabilization point moves by computing the displacement velocity of the lifted flame base as denoted by a small value of the OH mass fraction isosurface. And we computed it along the stoichiometric mixture fraction. And so if we look at the conditional displacement speed, which is represented by the energy equation as a balance between diffusion terms and reaction terms. Here's reaction, and here's normal and tangential diffusion. And you can neglect this term with respect to CP. Then when we plot the flame index conditional on temperature, there's a crossing with 0 at this location, which is the triple point or the stabilization point separating the premixed branches from the non-premixed branch. And at that location, we also computed the displacement velocity and its budget. The displacement speed is shown by the dark black line here. And at the triple point, why isn't that? Okay. I should say at the triple point, which is right about here, we get a displacement, we get a speed of about 1.7 to 1.8, roughly in that range, at the triple point, based on the flame index. So these are on average. And comparing that then with what the theoretical prediction would be, is that the displacement speed should scale as the laminar burning velocity multiplied by the density jump, the square root of the density jump across the flame. And this is earlier theory that was given by Lignon and others, where rho naught and rho 1 here represent the unburnt and burnt gas densities, burnt densities at the stoichiometric surface. And so if we assume that there is no radicals and that it's just inerts upstream of, there are no reactions upstream of the lifted flame base, then you would get a laminar burning velocity of about 0.56 meters a second, which would give you a displacement speed based on this density relation of about 1.06 meters a second due to flow divergence effects. Now, however, we do have this cool flame reactive soup ahead of the lifted flame base, and so we can start to do some evaluations in a reactor. If you start at time t1 with low temperature presence of these intermediates, this methoxy peroxide or species, and you let it cook in time until T2 when you have hot ignition with OH appearing, you can vary that delta T time to determine the level residence time for that radical low temperature soup to build up. And so we looked at the flame speed if you didn't allow for any time for the low temperature soup to build up, and that would give a burning velocity at the stabilization point of 1.43 meters per second. And we found that somewhere between 0.8 and 0.9, I'm sorry, between less than half of the time it takes for the hot ignition to occur, we get a flame speed of 0.9 meters a second that gives us a burning velocity of the stabilization point that's very close to what we observe from the conditional statistics in the turbulent flame. And so we think that there is a significant role in accelerating the propagation or helping to stabilize that lifted flame in the presence of these low temperature reactions. So from this study, we found that we have two upstream branches, one due to NTC behavior and one due to low temperature heat release. And we see that there is a triple flame consistent with what you find in a non-heated co-flow that appears downstream, and that the radicals and heat produced during the first stage ignition enhance the laminar speed by about 1.6 to 1.7 in a mean sense, leading to a much higher triple flame propagation speed. So with that, I'll stop for today and entertain any questions or comments, and then we'll pick up again tomorrow afternoon. Okay. Yes.
So my question about the visualizations which you just showed, what were the resources? Did you have to use HPC resources for the visualization videos as well?
So we worked with another computer scientist who's a visualization expert, and he wrote custom volume rendering methods that allow you to render multiple variables at the same time, and also particle rendering. And those were done on, not on HPC resources, but more on a cluster. And we didn't, of course, we don't have the entire data set. We only have 2 or 3 species, right? Or less than 2 or 3 things that we're rendering at a given time.
So are these being done on the fly, or is like or are these videos rendered from the data which are being stored onto the?
We've done both ways, and so we have ability to do in situ viz, both volume rendering as well as particle rendering together on the fly, where it's embedded inside of the solver. Yep.
I have a question. Just now you play a video, but doesn't work. you mentioned that in the video there's a hotspot somewhere.
Yeah, so similar to what we observed from the DNS in the experiment with the chemiluminescence images, we also saw the appearance of a little hotspot that was disconnected from the lifted flame. And that little hotspot, once it ignited, would expand and merge with the main body of the flame.
My question is, how can you know this spot where, by what condition? Like temperature, or critical temperature gradient or something? What is critical condition?
For the hotspot?
Yeah.
So I think the important conditions for its appearance, as Masterakos had showed earlier, is that there's a so-called preferred mixture fraction where there's a minimum ignition delay time, right? And so in a homogeneous reactor. And so that's where you would expect ignition spot to first appear, where the mixing rate is very low. It's sheltered there so that it has the ability to build up radicals without having it be advected away. And just thermochemically, at a given ambient temperature and pressure, there's a minimum ignition delay time at a certain mixture fraction. And so you can expect that to also happen, which we saw from the DNS. When you do conditional statistics of temperature with respect to mixture fraction, you can see where ignition appears first on the lean side. I didn't show you the corresponding homogeneous ignition delay curve, but they are at the same location. So 2 ingredients. It needs to have the right mixture composition through mixing with turbulence, the ambient and the fuel, and it needs to be in a sheltered environment. So high mixing rate is not where you're going to see these hot spots occur until much later when they're very robust.
And do you think that geometrical shape will influence the hotspots in practice?
The geometry shape of...
The boundary condition and the geometry shape.
Sure. I think it'll have a big effect in the sense that it affects the mixture formation. So where you have rich, lean, stratified regions where it provides the mixture conditions that are ripe for ignition to occur. So if you had a curved shape or something, you may have reentrainment, right, which would modify the mixing characteristics and mixture formation locally. Yep. Other comments or questions? Yep.
You show us significant amount of results over there, but you haven't talked about turbulent chemistry models, which one you use for the DNS.
Okay.
You haven't talked about any of them, like, do you use all of them PDF method or any other stuff?
Are you talking about the chemical mechanism?
Yeah, like turbulence chemistry model.
Oh, we don't use a model because this is DNS.
Yeah,
So if you do large eddy simulation, then you have to incorporate a model for the turbulence chemistry interaction. And there are a lot of models, which I haven't talked about, like flamelet modeling or presumed shape PDF or transported PDF or linearity model. There's a whole host of models. But many of those models were developed under simpler non-premixed or premixed conditions, but they're not necessarily applicable when you have mixed mode combustion like I was talking about today, where you have partial premixing and it's propagating into an autoignitive mixture ahead of it. So it's still, I think, work to be done to understand how applicable those models are, or if they need to be modified, and so on.
Is there any experimental result to compare about experimental result? Is there any experimental result to compare against the modeling results?
In this work, we didn't compare with the experiments directly, but in work I'll talk about tomorrow, we did do a direct comparison.
So is there any experiments done regarding to the situations, the boundary conditions?
Well, so yes and no, and that's an area that I think needs further work because it's hard for experimental people to measure at the exit plane of a nozzle or something, or a bluff body, because there's all the extra complications of the solid piece of metal and the heat transfer losses and things like that we don't necessarily account for in simulation. And so they might be able to get like a mean profile and an RMS velocity profile, but they won't have detailed scalar measurements. And experiments can only measure, major species along a line. They can't get a whole spatial distribution. So it's very difficult to get a full characterization from experiments for the upstream boundary conditions.
But how do you know the results are right?
How do I know they're right? Well, they're right. No, I don't know that. Yeah, right. So, so I think we do see qualitative agreement with what people observe experimentally, both in laboratory experiments and also in engine measurements. Quantitatively, we can't make that comparison yet. And I think if you look at statistics and kind of look at the theory, the different types of theory that are out there, we see very consistent behavior. So I can't say for sure that we're right. I know from the turbulence standpoint, we resolve all of the scales and we have very accurate space and time discretizations. The part that I'm less certain about is the chemical mechanisms and the accuracy of those for predicting ignition delay and for predicting flame propagation speed and structure. The mechanisms have been validated under lower dimensional conditions for reactors and shock tubes and flow reactors and for counterflow flames, right? That people measure in Bunsen flames, they measure turbulent burning velocity as a function of equivalence ratio. So to that extent, the mechanisms have been validated. Whether those properties change somehow when you have a different trajectory through turbulence is unknown. I kind of doubt they do, but I can't say for certain, for sure.
So how compatible is DNS with detailed chemistry to DSMC, for example?
How bad was the DNS?
How compatible is DNS with detailed chemistry with something like DSMC, for example?
With the direct simulation Monte Carlo?
For such small scale problems.
Okay, so this, first of all, DSMC has not looked at detailed combustion chemistry. It's been used in the past to look at rarefied flows for reentry, right? So for nitrogen, dissociation of nitrogen, oxygen kinds of reactions, diatomic species at different kinds of conditions, not at flame temperature and not with the flame species. So I think it's still not possible to compare. And also DSMC is not, the domain sizes, well, it's now can run on petascale machines and is parallelized very efficiently. It cannot, it's just now starting to see hydrodynamics coupled with chemistry. And the simplest chemistry, maybe just one or two reactions, not a full-up mechanism like we're using in the continuum. We hope that direction will grow, because I think there's a lot of interesting physics that is not continuum that can be explored with these particle simulations, but we're kind of at the beginning stages of that, I think.
I was wondering what your on-the-fly stiffness removal method is. What do you do for that?
I would have to defer to Tin-Fun Liu, who developed it. But he's looking at timescale analysis of the diffusion flux terms compared with the chemical timescales from the Jacobian, reaction rate Jacobian. And then he's doing something there, but I'm not sure what. But there is a paper on it I can refer you to.
And have you considered, or have you even seen the necessity of considering more sophisticated techniques like dynamic adaptive chemistry?
I think that would be interesting, but I'm not sure if the benefits outweigh all the complications and potential loss of accuracy where you're at the interfaces where you're adapting. But I think it's worth looking at, and I think people have looked at that. So we already adapt the mesh locally, but we haven't adapted the chemistry, and I'm not sure if you would just still always transport the same number of species, but change the number of reactions that you compute locally. And then how would you transition spatially if you have strong, steep gradients or jumps, not to impose a bunch of numerical errors?
I think you adapt the dimension of the transported composition as well.
Both.
Yeah.
Yeah, so there, maybe you can use a method like adaptive mesh refinement does now, where they coarsen and refine the mesh and do some kind of interpolation. But what that actually does to the underlying physics and dissipation, I'm not really sure. Are there any other comments or questions? Otherwise, we'll pick up tomorrow, and I'll show you some other classes of problems that we've looked at. Okay, thank you.